Okay, here I have a wire. It's a long wire. I'm not going to fool you into thinking that it's infinitely long, because obviously you're not going to believe me. And it's not infinitely long. But let's say that it's very, very long. Now I can rotate this infinite wire. Still don't believe me that it's infinite. Okay, switching its ends. It doesn't look any different than it did before. It's still effectively the same wire, assuming that the wire is completely uniform. I can block your view. Okay, watch this. Now I'm blocking you. Okay, now, you tell me, did I rotate it or didn't I? You can't tell. If this wire has a uniform charge distribution, say, well, like the charge distribution we're going to use here in a minute, 7 times 10 to the negative 8th coulombs per centimeter, then when I rotate the wire, it still has a charge density of 7 times 10 to the negative 8th coulombs per centimeter. We still have a long wire with the same charge density. And if you're not looking, or if you can't see when I rotate it, you can't tell that it's been rotated. Now, I've got just a finite section of a similar infinite wire right here. And to the end of this wire, I've taped, I didn't tape it, actually it came this way, with a tag. Okay, that tag is simply the tag that they scan in the checkout line. Now, if I rotate this wire, we can tell that it's being rotated. We can tell by the tag. If I hide the tag so you can't see it, well, I guess you can kind of see it, but can you tell? If I hide the hand that's doing the rotating, let's see if I can do that. You can probably tell by the fact that it's moving, but you don't know if I'm moving it or rotating it. Okay? If it's a completely uniform wire, the point is that if I rotate it through 90 degrees, 180 degrees, negative 30 degrees, whatever, it still remains a wire with 7 times 10 to the negative 8th coulombs per centimeter on it. And if I rotate this infinite wire, okay, let me get the infinite wire again. Okay, here's the infinite wire. If I rotate this infinite wire, except by watching my fingers, you can't tell that I'm rotating it. If I come over here and rotate it, you probably can't see. Of course, the wire's flopping around a little bit because I can't hold it steady. But you can't see whether I'm rotating it or not. So that whether the wire is rotated or flipped end over end, it remains an infinite wire with a charge density of 7 times 10 to the negative 8th coulombs per centimeter. That argument is going to show us that the electric field that comes off of this wire, I'm using the finite wire now, the electric field that comes off of this wire is going to have to be perpendicular to the wire at every point. And if you look at the wire end on, the electric field is going to look kind of like a pincushion, so that it's independent of symmetry. That is, the electric field comes off equally in all directions as the wire is viewed from the end. Now, given that situation, if I take the wire and slip over it a cylinder, okay, now I'm slipping the cylinder over the infinite wire. You can wonder how I got it on the end, since the wire is infinite. But here's a finite cylinder. Now, I position that cylinder so that the wire is right along the axis, the central axis of the cylinder. Now, I can't really do that very well. Actually, I can do that fairly well, but I'm cheating. You can't see it on the paper, though. I mean, on the camera. Okay? So let's imagine that the wire is right through the axis of the cylinder. Then the electric field is coming off of the wire kind of like bristles off of a brush, coming perpendicular to the wire and all the way around the wire, just kind of surrounding the wire like bristles. And that electric field is going to penetrate this cylinder only along the curved portion of the cylinder. Okay, only along the curved surface of the cylinder, provided I can keep the wire in the center. Similarly, I can slip a larger cylinder over the end of the wire. Okay, so there's a large cylinder with the wire right through the axis in the center. It's not a particularly uniform cylinder. Let's make it look a little more uniform anyhow. Okay, if the cylinder is uniform, then again the electric field penetrates the cylinder because of its direction only through the curved surface, not through the ends of the cylinder. Now this cylinder is larger than the one before, so we have a greater density of electric field lines through this cylinder than through the other. And that means there's more electric field through the smaller cylinder than through the larger. Looking at the mathematics of the situation, if we have a long wire with a charge density of 7 times 10 to the negative 8th coulombs per centimeter, and we put a cylinder of radius 2 centimeters around this wire, and the cylinder has a length of 10 centimeters, then the total charge inside the cylinder is going to be the 10 centimeters times the 7 times 10 to the negative 8th coulombs per centimeter. I lost the C in my centimeter there. Or 7 times 10 to the negative 7th coulombs. If the cylinder encloses 7 times 10 to the negative 7th coulombs of charge, then the total flux through the cylinder has to be 4 pi k times this charge, 4 pi k q. This is the principle that we're using here. So that by finding the charge enclosed inside the cylinder, I can tell what the flux is through the cylinder. So in this case, the flux is 4 pi k q, where q is the 7 times 10 to the negative 7th coulombs. Well, the flux also equals the electric field times the area of the cylinder. And as we saw when we did the flux picture for gravity, the area of the cylinder is just the circumference of its cross-section, 2 pi r, times its length. The cylinder can be unrolled into a rectangle of dimensions 2 pi r times L. And that turns out to be 0.0125 square meters. So that the electric field times the area equals a flux. We know the area, we know the flux, we can find the electric field. Electric field times your 0.0125 square meters is 4 pi k times your 7 times 10 to the negative 7th coulombs. We easily solve for E, plugging in the 9 times 10 to the 9th Newton meter squared per coulomb squared for K, and find that the electric field is 61,600 newtons per coulomb with a question mark. Now that's a calculation I did in class. I don't swear to its accuracy. You should check it. If you come out with something a little bit different, then that means I made a mistake. It's always fun to catch me in a mistake. But the whole point of leaving that unverified is just so that you will verify the calculation.